Okay, hello to everybody. So we keep on studying our problem. So I recall you where we were. This was the problem given. Sorry, no. So given a fluid with uniform density equal to 1 in some units. So we don't have to add some density factor. This is you can really get rid of this statement. But the velocity is this one, is this vector field, and we want to compute the flux of the fluid through the portion of the paraboloid, and this is the paraboloid. Oh, we gave a picture. This is the paraboloid, and then I stressed very much, perhaps in a too a pedantic way, that we have to pass from the Cartesian description of the paraboloid to the parametric description of the paraboloid. Okay? And since the surface is given in the form of a graph, it is very easy. We put the parameter u equal to the coordinate x, the parameter v equal to the coordinate y, and then z inherits its shape by the Cartesian equation. Okay, so z is equal to u squared plus v squared. Now, with these parameters, we can easily write down the vector position, the vector of the generic point on the surface. So we have u, the component I, v is the component j, and u squared plus v squared is the component k. And the domain is given, of course, by z less or equal to 1, which in terms of the parameters becomes u squared plus v squared is less or equal than 1. Then I told you and I illustrated you what is the geometric meaning of the derivative of the vector r of the position on the surface with respect to the first parameter and with respect to the second. These are just the two vectors tangent to the curve corresponding of the motion of the point on the surface when only one of the two parameters is valid. These two vectors, if the surface is regular, happen to be non-parallel. So, since they are non-parallel, they generate a plane, which is the tangent plane to the surface, and so they're orthogonal. It's only one direction, and it is the direction of the normal vector, and it is easily given by the cross product of these two derivatives. In this case, this is the cross product. Okay? So now, the definition of the flux is the following. This is very important definition, so I put it in red. Flux is equal to F dot this vector n and then d sigma, where this is the general formula, and of course this is on the surface sigma, which is the paraboloid, where F is the field, so this is the field, and n is nothing but the normal vector. And geometrically, this quantity n d sigma can be written as dr du cross dr dv du dv. Okay? So what is the geometrical meaning? Let me get rid of this. Geometrically, the quantity n d sigma is the element, the area, be more precise, the area of the element of the surface. But be careful, because it is a vector. It is not a scalar, it is a vector. So along the direction of the normal vector. So, for instance, if you are here, the normal vector is chosen to go upward, so it is inside, but the vector n d sigma has the modulus of dr du cross dr dv and the direction of n. This is the message, okay? If you need more theory for that, I can give you more theory for that and more understanding, but I'm quite confident that you already studied it with Professor Cudratillo. However, I'm here, I'm available for other explanation. Here I want to move forward, and so now write down the flux as f in terms of the parameter u v dot dr du cross dr dv du dv, where u and v now don't move on the surface, but move on the space of the parameter d, which is a subset of R2. Okay, this is d. So d is not sigma. D is the space occupied by the parameter, so it is a two-dimensional domain. Sigma is the surface, and this sigma is a subset of R3. Okay? Be very careful on the conceptual, on the ideal difference between these two notions. Okay, and now compute this quantity, just use the parameter. So here you have integral on d of this field. The field is yi minus xj plus k. Yi minus xj plus k has to be written in terms of u and v. Dot, it was minus 2ui minus 2vj plus k. So, and this is, sorry, in du dv. And this is equal to vi minus uj plus k dot minus 2ui minus 2vj plus k du dv in d. And now just compute the dot product. So we have to consider the product of the equivalent coordinate and then sum them up. So we have d minus 2uv. Then there is the j coordinates that give you 2uv plus 1, and this cancels, it remains +1, du dv. So it is just the integral of 1 in the domain D, so this is the area of D. And what is D? So D is defined by u squared plus v squared less or equal than 1, so this is nothing but the area of the circle of radius 1, so this is pi. Very easy. And so this is the flux, okay? So the main formula you have to remember is this one, and then it's a matter of computation. So the recipe, if you want to write down a recipe for computing flux, so recipe for the direct computation of the flux first, write down the surface in the parametric form. The parametric form. Second, compute the normal vector at every point of the surface and choose the prescribed orientation. So obviously, if the orientation is not the prescribed one, it is the other one, then the flux changes sign. Okay, you are looking at the flux in one direction or in the other direction, so just the sign changes. Okay, 3, compute the integral. And the integral is always the same, which is f on the surface sigma scalar n d sigma, which is the integral on the domain of the parameters of f as a function of x u v, y u v, z u v times what? In parametric form you end up with r u v. So this is dot dr du vector dr dv. Of course, I don't want to put parentheses here because it is clear when you have a mixed product where you have a dot and a cross. First, you always do the cross and then the dot, because otherwise, if you first do the dot, then you are stuck. You cannot do the cross. So there is only one way to do this product. First the cross and then the dot. Okay, so I write it like that, and this is du dv. Okay, and this can be quite long, and I want just to give you such a sort of cultural example. And so this is a very important example. Important example is the computation, the flux of the electrostatic field generated by a point charge. Okay, the field of a point charge is the following. So the field of a point charge is E equal to the charge, which is Q, divided by R squared. R squared is the distance from the point Q, so this is E of R. The direction is R, so the fact that it is outgoing or ingoing just depends on the sign of Q, and then there is a constant here, which is a huge constant in the standard international unit, but it is irrelevant for our exercise. Okay? And so we want to compute the flux through a spherical surface surface of radius R centered at the charge. So the picture is the following. Here you have a charge Q, and then here you have a sphere. A radius R, and here you have stop and here you have let me be a bit less precise, but just to give you the idea of a sphere. Okay, this is a sphere, and then Q, if the charge is positive, then you have this field, and this field points out. And so you have that this field is uniform. So on the sphere as intensity. So that if we have the flux, which is the integral on sigma of E scalar n d sigma, so you can extract a constant part here, which is kq over r squared. Yes. And here you have just in sigma r scalar n d sigma. Sorry, r is a unit vector, but r and n are parallel. Oh, sorry, this is capital R, because here the sphere has radius capital R, as for the exercise. R and n are parallel, so here you have k q over r squared, and here you have modulus of n d sigma on sigma. But remember that this is nothing but the element of surface of the sphere. So when you sum up over all the sphere, all the element of surface, then what you gain is the area of the sphere. This is nothing but the area of the sphere, which is 4 pi a square. So what you get at the end is 4 pi k q. And this is first amazing fact. The first surprise is that the flux does not depend on r. Does not depend on the radius. You can take the sphere to be very, very large or very, very small, and the flux is always the same. The reason is quite clear, because the surface grows as r square and the field goes as r to the minus 2. So there is an equilibrium. The second surprise is more surprising, to be proven separately. And we will see a bit of it. The flux of such field around through a surface containing the charge Q is always, it was 4 pi k q. And the third surprise, which is in general, whatever is the distribution of charges, so not only pointwise charge, then what happens is that the flux of the electric field, electrostatic field through a surface, a closed surface, always equals four pi kq, where q is the amount of charge inside the surface, enclosing the surface. And this is the content of Gauss' theorem, which is very important. You will see it at physics 2. So first comes from our computation. Try to redo this computation by parameterizing it. The second, okay, we will see it after studying divergence theorem. Third, so in the third is content of the Gauss, and so you will see it in physics 2 course. And now I stop here.